Hello, welcome to another video for General Science. In this video we're going to be discussing work. And this is work in the physics sense. So it's a little bit different than what you might understand in the traditional. This is a little bit more specific, okay? So recall that objects move when an unbalanced force acts on them, or on it. Work is a product of force and distance. So you apply force to an object, and when you apply that force, you apply it in such a way that it's an unbalanced force, overcoming whatever other forces are keeping it from moving, and then you move that object, okay, you displace it, you create a distance, and it is a product of that distance times the force that is applied. Okay, so force and distance must act in the same direction. Otherwise, you're not really moving. So again, force and distance. Work is a function of force times your distance. And again, this is assuming that the force is working in the exact same direction that your distance is changing. Otherwise, if you're applying your force at a different angle, like let's say when you're mowing a lawn, you're not necessarily pushing exactly in a parallel direction as your distance. Your force is actually being applied at a certain angle. And whenever you have forces that are applied at certain angles, the equation goes from being a simple W work equals force times distance to W force times cosine theta, which is the angle of the force, times distance. This video we're not going to deal with any problems that are having to do with working out the angles of which the force is applied. Here we're going to assume that the force applied is exactly parallel to the direction of the distance that's changing, giving us, again, this equation. So we'll be working with a very simplified version of work. Okay. Later on I'll make videos where we're applying forces at different angles to objects. Okay. So continuing on with our discussion, we have here an example here of force being applied on weight. Okay, this is 94 kilograms, clean and jerk. Okay, it's a power clean. So we need to find our force, which is 94 kilograms times the force of gravity. That's our weight, right? So notice that the force was up, so the distance is up as well. So our force times distance would apply in this case. And we find our force using our weight formula. So this would be the total distance that the object has changed. So it went from being on the ground to all the way up to where the man power cleaned it up. Okay? So let's use our equation here. So work equals force times distance. And we found out that the force of the object are using our weight. So we have force and distance. Those are the two units that we need to find. And force we found, again, via our weight equation, which is mass times gravity, is 921.2 newtons. And our distance, let's just assume that our distance was 3 meters. So now that we have a force, and our force was applied in the exact same distance that our distance changed. I'm sorry, our force was applied in the exact same direction that our distance changed. Okay, so we multiply our two terms together, and we end up finding that 2,764 newtons per meter, or newton meters, of work was done. Okay, let's look at another example here. So here we have a man pulling on a Hercules aircraft. Okay, the strongest man competition. Again, we find out our weight by our mass times gravity, and the mass of this object was 40,823.3 kilograms multiplied by the force of gravity, giving us 400,068.34 newtons of force. Okay, or 4.4 times 10 to the fifth newtons. So that's the force. We found our F. So now that we have our F, we need to find our distance. And as it turns out, this guy was pulling this aircraft 25 meters. Okay? So we use our force times distance, giving us 1 times 10 to the 7th Newton meter. Okay, so that's a lot of work that man did. So one last thing before we move on, now that we've done our equation here of work equals force times distance, and you've seen how it works, let's talk about the units of our equation. Okay, so you know that force is in the units of newtons, and our distance is in the units of meters. So when we combine these particular units, we get what's called a Newton meter, or a joule by capital J. Okay, so this is a joule of energy. This is the unit for energy that is being used to change the direction or the displacement of an object times the force applied to that object. And this unit was derived by our friend here, James Prescott Joule. From 1818 to 1889 he lived. Okay, so that does it for our discussion with work, and we'll work out some examples in class. So good luck with your studying.